All right, it's that time. So what we're going to be looking at is polar coordinates today. So Cartesian coordinates is our normal coordinate system where you move um, left, right, and then up, down. Polar is just a different way of looking at moving to a particular location. So slide 3 here, we have our video, and this is the normal way of moving to the location 4, 4. We move right 4 and then up 4. So we sometimes call this rectangular because we're moving um, along the sides of a rectangle or square to get to a particular point. But if I was actually going to move to that point, like shortest distance possible, I'd turn 45 degrees and then I'd just walk that distance out to that location. And that is how polar coordinates work. So polar coordinates are written r comma theta, but we usually think about the theta first. So you rotate a number of degrees or radians, but you turn to an angle direction, and then you move however many units out in that direction. So this new system is called polar coordinates. So in the system, the origin is called the pole. So that's part of where polar is coming from. And then it says here, if the radius is positive, then r is the distance from the point to the pole. So we can actually have a negative radius, but so typically though our radius is positive, and then theta can be in degrees or radians. Usually it's going to be in radians. And then the ordered pair is written r comma theta. Now, if the angle is in radians, but it's not in terms of pi, we can actually have a polar point that looks similar to a rectangular point. And I think there's one on the writing assignment that does that. So anytime we're dealing with a question and they give us an ordered pair, they're going to tell us if that ordered pair is a rectangular or a polar point. So they're going to call it either an XY point or an R theta point. Now, when we think about graphing these points, instead of our normal XY grid, we have this spider web grid, or that looks very similar to like a sonar or a weather radar. So our 0 degrees or 0 radians is still the positive x-axis. And then we can see the grid here has circles. The circles are radius rings that are measuring the distance from the pole. So we can see our A point here is on the 2 ring. So the radius to get to A is 2. So that's why all the ordered pairs have a 2. Then the other thing the grid has is radial lines. And these lines are marking the angle measures. So we see the angle line that A is on is at pi over 3. So that location is 2 comma pi over 3. Now, if our radius is negative, we're going to still turn our theta direction, but instead of walking forwards in the direction we're looking, when the radius is negative, you move backwards. So you'll still be looking in that direction, but you'll walk backwards whatever the radius is. So this positive or negative on the radius determines whether we walk forwards or backwards. So here's an actual example. So if I had the polar point -4 comma pi over 4, the angle pi over 4 is in quadrant 1. So that's the direction we're looking. But when the radius is -4, instead of walking 4 into quadrant 1, we're going to walk backwards 4 units, and we end up in quadrant 3. Now, another interesting fact about polar points is that there's more than one ordered pair that describes a location. So in our rectangular system, our XY system, when I pick a pair of numbers, then that only goes to one location. And there isn't another set of numbers that will get me to that same location. It's only that one pair. In polar, though, because of the way the angles work and that they can be coterminal, there's infinite angles that will get you to the same position. And because of the way negative radiuses had to work, there's also a secondary list of points with a negative radius that would also get you to that point. So right now we're seeing this point, -4 comma pi over 4, is in quadrant 3. But if I wanted to know what's the coordinate to get to that point with a positive radius, I have my original angle of pi over 4, and then to that I'd add pi. So I have my pi over 4, and then I add pi, and this location down here is also at 5 pi over 4. So if I am at 5 pi over 4 for my angle, my radius at that point would then be the +4. Now, because of the way coterminal angles work, -4 comma pi over 4 is equivalent to any coterminal angle to pi over 4. So -4 and pi over 4 plus any 2 pi k. On the other side, with my positive radius, then it would be coterminal angles with 5 pi over 4. So we have two infinite lists of points that all would just map that single location. So an infinite list of numbers, but they're all describing that same particular point in the coordinate plane. So this is why we don't use polar that often. But in certain situations, polar is more advantageous. Polar in particular, like a really common application is actually in 3D graphics. If you think about like first person perspective, you're looking like left and right, and then you look up and down. So that's two angles. So those two angles are a way to get a 3D polar perspective. And then if you're doing a first person shooter, you have your two angles, and then you have the radius is how far the bullet's going to go. So that's one of the ways they can calculate it. Or if you're shooting like a bow and arrow in a game, they have the two angles that you're pointing at, and then they can track the arc that the arrow would make. So it wouldn't be a perfect radius because it'd be an arc, but they use that initial two thetas to get the direction. So our next slide is just listing the generic formula for the two different radiuses. So if I have a radius and my theta, and it could be any plus 2 pi k, an equivalent point, if I change the radius to negative, would be to have the angle plus pi, and then it could be plus the 2 pi k. So when I'm looking at a positive or one particular setup, if I want to change the sign of the radius, I have to add pi to the angle. And then I have my alternate way of writing the point, and then I can add or subtract any coterminal angle to get equivalent points as well. So that's what our next slide is asking us to do. They're giving us the polar coordinate point 3 comma pi over 6, and they're asking us to come up with equivalent polar points. So our first point, they're saying the radius is positive, so that means the radius has to be positive 3. There's no other number I could put for the radius to keep this location the same. But they want us to have an angle that's bigger than 2 pi, but smaller than 4 pi. So we're going to take our initial angle of pi over 6, and then we're going to add 2 pi to it. Now to get my common denominator, I multiply by 6 over 6. So this is 12 pi over 6 plus a pi over 6 gives us 13 pi over 6. Now our next one says make the radius negative. All right, so I'll start typing that in with the negative 3. And then they want the angle to be between 0 and 2 pi. Now the angle has to shift to account for the negative radius. So I have my pi over 6, and then here I'm going to add pi. So that's because the negative radius, we're going to move backwards. So I need to not look at pi over 6, but I need to look at the angle that's backwards, the opposite direction. So I add pi radians. And then again, we multiply by 6 over 6. So that gives us 7 pi over 6. Then our last point is back to a positive radius. But now they want the angle to be less than 0, but bigger than negative 2 pi. So I'm still going to start with my pi over 6. But if I want something less than 0, instead of adding 2 pi, I'm going to subtract 2 pi. So pi over 6 minus 12 pi over 6 is negative 11 pi over 6. So just remember that 7 pi over 6 is like, it's collinear with pi over 6. It's like, those are like kind of two opposite directions, but they're on the same line because they're 180 degrees off from each other. So we rotate to 7 pi over 6 and then move backwards to the 3. So there's our negative 3 radius with 7 pi over 6.
Excuse me.
Yep.
So what is the first one you put pi over 6 plus 2 pi equals 13 pi over 6.
Mm-hmm.
Um, what is the 4 pi there for? Or how does this relate to the equation under change?
So under change, they said keep the radius greater than 0. So the radius is positive. And then they said give us a theta that's bigger than 2 pi and less than 4 pi. So 13 pi over 6 is bigger than 12 pi over 6. 12 pi over 6 is the same as 2 pi. 24 pi over 6 is the same as 4 pi. So 13 is between the 12 and the 24. So 13 pi over 6 is the angle that's between those two boundaries.
Oh, okay. So but wouldn't like another pi? So another pi would be 19 pi over 6. Would that still work? And it'd be negative 3?
It would be negative 3, but then it wouldn't be satisfying the requirement that they said the radius had to be positive.
Ah,
But
okay.
negative 3 comma 19 pi over 6 would also be another point that would get us there.
Only if it was um
Radius less than 0.
okay. And going another full pi would make it wouldn't fit the conditions, right?
Correct.
25. Yeah. Ah, okay. Awesome. Thank you.
Mm-hmm. Good question. All right. So in the past, we have asked a question similar to this on the test. Usually on the test, we give you the XY point and we ask for a polar point. But in the past, we've also asked for an equivalent polar point. So I don't know if we're still going to do that on this test or not. We're going to meet later today to finalize the test. So I'll be able to better tell you how that's going to look next time. So now thinking about that conversion between polar and rectangular. So when I have my drawing here for my r theta point, and if I put back in there the xy point, like those are two different ways of talking about the same point. But when I'm looking at the picture here and I draw in that right angle, I have a right triangle. My x side here, the x distance, is the adjacent side. The y side is the opposite side. And then the distance labeled r is the hypotenuse. So if I want an expression that relates x with r and theta, then I want to pick the trig function that deals with adjacent and hypotenuse. And that trig function is cosine. So the cosine of theta is x over r. And then if I multiply by r, I get the equation they put in the box, x equals r times the cosine of theta. So if I have my polar point, my r and my theta, I just do r times the cosine of that theta, calculate that, and that gives me the x coordinate for the rectangular point. Now, similarly, if I want an equation that relates y to r and theta, then I'm going with sine theta. Opposite is y over hypotenuse is r. So sine theta equals y over r. And then I would multiply both sides by r. So I end up with y equals r times the sine of theta. So if I wanted to know the y coordinate for a particular polar point, I do the radius number times the sine of the given angle. Calculate that, and there's my y coordinate. So I'm going to give you this formula on the test. I'm not going to label it as polar. So you do have to remember that the last little equations on the formula sheet are the polar equations. But it's a set of 4 equations. So now let's see this in action. Let's see what it looks like when we actually start doing a calculation with this. So they just gave us a point out of nowhere, and they're wanting us to do a conversion between rectangular and polar. So the way these questions are typically written, they will tell you explicitly that a point is polar or rectangular. Here, we're going to assume it's polar because they are saying write your answer as an ordered pair x comma y. So we're going to assume 6 pi over 6 is a polar point, but that means it's an r theta point. So that's one of the first things I like to do is just to make sure I remember how those numbers are being labeled. I write it down. R comma theta is 6 comma pi over 6. Now my x coordinate is r cosine theta. So I'm going to fill in r is 6. Cosine theta is pi over 6. Now you'll have the unit circle on the test, but we look up pi over 6, and that is long coordinate first. First coordinate is cosine. So our x is 6 times the square root of 3 over 2. And then the 6 and 2 reduce, so we get 3 square roots of 3. Then same song, second verse for our y coordinate, our sine theta. So it'll be 6 sine pi over 6. The sine of pi over 6 is the short side, so 1/2. And 6 times 1/2 is 3. So we type that in as 3 square root 3, comma 3.
Excuse me.
Yep.
So is mm, so it says 6 cosine of pi over 6.
Hmm.
Could you ever replace pi over 6 with like the angle, the corresponding angle or something?
Well, that is the angle they gave us.
I know, but would it just I'm just curious, would it just come out different, or would the answer still be the same if I did 6 times cosine of 45 degrees
Well, 45 isn't the same as pi over 6, but if you traded it out
or
for
30
30
degrees?
degrees, yeah, you
Yeah.
could do that. You just have to make sure your calculator is in degrees mode or radians mode, depending on which one you type in.
And it would give me three square roots of 3.
Yep. Now, I might give it
Ah,
to you as the decimal. So if you just type cosine pi over 6 or cosine 30, um, if it doesn't give you square root of 3 over 2, then what it does give you is 0.866. And then you can just remember 0.866 is square root of 3 over 2. Like all of our unit circle angles are giving you either 0 and 1, zero point 0.5, 0.707, or 0.866. 0.5 we remember is 1/2. So it's just remembering that the zero point 0.7 is square root of 2 over 2, and the 0.866 is square root of 3 over 2.
okay. So it would say 3.866,
No, because
or not 3.8. It would say, what would it say for 3 square root 3?
so I think it's actually like 4 point something as a decimal. So you'd want to type it in like in pieces. So if I type in 6 cosine pi over 6, I get actually 5.196. So that's like a crazy number. I can't tell if that's some square root of 2 number or some square root of 3 number. So I take out the times 6. The cosine of pi over 6 on its own is the 0.866. So I'd trade that out for square root of 3 over 2. And now I'm doing 6 times the square root of 3 over 2. And if I type that in, it'll give me the same 5.196. But I
Oh,
can
but
see if I'm doing
there's
it
no
by
way.
hand. Go ahead.
There's no way to like a second answer on the calculator to get 3 pi over 3, or 3 square roots of 3. So like when you
Um,
get that 5.16 number, you can't second answer it to get the 3 square root 3.
it depends on your calculator. Some calculators can convert it back to 3 square roots of 3. Some calculators, like my phone calculator, is too stupid.
Yeah. Okay.
All right, so if we look at plotting this point, 6 and pi over 6. All right, so plotting our XY point puts it here, a little bit bigger than 5, comma 3. Our R theta point says that this distance is 6 units and that this angle is pi over 6. Now, looking at the picture, that angle looks closer to 45 degrees, but if you look at the grid in the background, you notice that the grid is not squares. They're actually slightly elongated, tall rectangles. So that means this drawing is not to scale. Because the grid is not a square, it skews what our angles look like. But getting Desmos to produce a square grid is not as easy as you would think. But still, we can make sense that this distance here, the 3 square roots of 3, and then this distance up, just 3 units, that if we Pythagorean theoremed those two, we would get 6 as the result from the Pythagorean theorem for the hypotenuse. and seeing the 3/6 for the opposite over hypotenuse, that's 1/2. That matches our sine of pi/6. So even though the picture isn't to scale, like the relationship of all the numbers does check out. All right, let's see the next slide. So plotting points in Desmos can be awkward when you're dealing with polar. So when you're looking at graphing on Desmos, the graphing calculator, there is this wrench icon in the top right. And one of the first things that opens up is grid. And there's two different options for grid. The first one that looks like a mesh, that's our normal XY coordinate system. And then the one that looks like a spider web or a bullseye, that's our polar coordinate system. So it just changes the background. So we're going to leave it in polar. So we can see this point we have here is at radius 6, and the angle is 30 degrees. So I can, when I type in like my rectangular point, it plots that point for me just like it's an XY point. But if I tried to type 6, 30 or 6, pi/6, it would plot that like it was a rectangular point instead of a polar point. So the only way to get Desmos to plot polar points is to use this workaround where we type in r cosine A, r sine A, and then underneath it, we label what A and R are going to be, are equal to. So if I wanted to know what's the point that is like a radius of -3 with an angle of like the 30 degrees there, then I can see that's in quadrant 3 now, because we're on our pi/3 line, or pi/6 line, which is our 30-degree line. But we've moved back into quadrant 3, -3, that's halfway between the 2 and the 4 rings. So you can use this slide to plot a polar point just by typing in the angle and the radius. Or just using that r cosine A, r sine A setup, and then just type in A equals and R equals, and it'll plot the point for you. So just while you're getting used to how do these polar points work, this is a slide you can use to type in the numbers and see where it ends up. And you can zoom in or zoom out if the numbers get really big, but they should stay on this grid. I don't think we give you radiuses bigger than 10 on anything. All right, so now they're being a little extra. They're giving us all negative numbers. But same calculation. So again, I still like to start by labeling my point. This is a polar point, so it's an r theta point. So r cosine theta is -4 cosine -pi/4. So that is -4 times the cosine of -pi/4. If I go look on the unit circle, -pi/4 isn't technically one of the unit circle angles. It's coterminal with one, but it's not on there. So if you're like, I don't remember exactly what this is, just type in cosine of -pi/4 on your calculator. And some of your calculators will spit out square root of 2/2. but the stupider calculators will spit out the 0.707. But we can see here that it's positive 0.707. And then I just have to remember that that 0.707 is square root of 2 over 2. So I used my calculator for an angle that was not normal unit circle and still produced what the unit circle ratio would be. And then I can just finish the calculation. The divide by 2 into the -4 will give us -2 square root of 2. And then same thing for our y coordinate. Our
Excuse
sine.
me.
Yep.
Is there any way that the negative angle or the negative theta would wouldn't correspond to the exact um xy value if it's negative? So like if it was like negative pi over 3, is there any time it wouldn't correspond to 30 degrees or square root 3 over 2 or 1/2?
So as long as they're giving us angles that are coterminal with unit circle angles, it'll always be one of the numbers from the unit circle chart. But if they're giving us like, 70 degrees, well, I don't have a pretty square root answer for 70 degrees. So then I just use the calculator and do -4 times the cosine of 70 degrees, and it would spit out a decimal, and that decimal is all I have. I wouldn't have an equivalent square rooty answer. But on the homework and on the test, we're going to give you angles that are on the unit circle.
Mm-hmm.
But in reality, like they very rarely are unit circle angles in actual examples. Usually they're ugly numbers, and all you get with your trig functions is just you do the sine of that or the cosine of that and write down the decimal.
What about converting the decimal into a fraction?
They don't convert to a fraction. They're ugly, irrational numbers.
Uh,
Like the
well,
only one that converts nicely is when it's 1/2. Like there are really ugly angle numbers that convert to nice fractions, but usually if the angle looks like it's an integer, then the sine and the cosine are ugly decimals.
okay. Thank you.
So if we type in the sine of -pi/4, the calculator will tell us -0.707. So this is negative square root of 2 over 2. So now this is going to be positive 2 square roots of 2 for our y coordinate. So if I'm going to plot the -4, -pi/4, so -pi/4, that direction is in quadrant 4. But then the radius -4 actually moves us backwards into quadrant 2. Now, if I look at my xy coordinate, my x coordinate was -2 square root of 2, and my y coordinate was +2 square root of 2. So we can see our xy is correctly corresponding to quadrant 2, even though our polar point we had to think a little bit more to realize it was a quadrant 2 point. But the xy point, like the numbers, what we see is what we get. Those numbers that come out of the calculator are for sure the x and y coordinate. Now, there are other polar points that could get me to the same xy coordinate pair. Like if I made it +4 for the radius, then I'd convert the angle to positive 3 pi over 4. And that would also go to the same location. And if I use my XY formulas, it would spit out the same results, even though the numbers going into the formulas would be a little bit different. But the sine and the cosine take care, the formula will take care of everything, so the XY coordinate comes out the same, regardless of which polar coordinate you use.
Excuse me.
Mhm.
So the angle would be 3 pi over 4.
If we were using positive radius, like this is equivalent to the point they gave us. I change the radius to positive and I add pi to my angle. That's an equivalent polar point. Both of those
Oh,
calculations would give us the same XY coordinates, though.
well, you see how on the quadrant 4 it's negative pi over 4. What would the quadrant 2 angle be?
3 pi over 4.
Oh, but the radius is negative 4,
So with
or
negative
the
pi over 4, we're looking in quadrant 4, but then we walk backwards and end up in quadrant 2. With the alternate point, we'd turn and look to 3 pi over 4, and then we'd walk positive 4 and end up in quadrant 2 at the same location.
wait. So why does the radius
Why does the radius?
for the hypotenuse? Why does it say negative 4?
Because originally I was plotting the original negative 4, negative pi over 4. So the negative 4 is also implying the direction. Normally, when we draw a right triangle or any triangle in the unit circle, the hypotenuse is positive. But in polar coordinate systems, sometimes that radius distance is negative to imply the direction we went.
So to get this triangle, it would be I'm just kind of spitting out words, but it would be the inverse of negative 4, negative pi over 4. And we would get 4 comma 3 pi over 4.
So to get not an inverse, but an equivalent point, we could get those two, but they're not like, there's not a function that'll switch between them on the calculator. They're
Uh,
just two equivalent polar points. So if I change the radius to positive, then I add pi to the angle, and that gets me to the same location. I could also take either of these points and add or subtract 2 pi to those angles, and those would also be alternate polar coordinates that get me to the same location.
what's that location exactly? At what point? Is it the end of the triangle?
Yeah, the end of the triangle. So the negative 2 square root of 2 left, and then the 2 square root of 2 up, that physical point in the coordinate system, that's the location we're talking about. All of these are just different ways of describing that particular point on the plane.
And that point equates to 4 comma 3 pi over 4.
Or negative 4 comma negative pi over 4.
Ah, so there's no point at the quadrant 4 at the end.
Yeah, because of the negative radius, instead of moving into quadrant 4, we always move back into quadrant 2.
Oh, okay. So it's kind of like the like how we do inverse of cosine, inverse of sine. It always we kind of always have to go backwards into quadrant 1 or 2.
Kind of. We could have like negative 4 comma like 7 pi over 6. So 7 pi over 6 would be looking in quadrant 3, but then with the negative radius, I would end up in quadrant 1.
Instead of going to quadrant 2.
Right. So it's always the 180-degree opposite.
Oh, okay.
So it's just quadrants 2 and 4 are 180 degrees opposite, but 1 and 3 are also 180-degree opposite. So if we just had a different point that was in one of the other quadrants, that's where we'd end up.
Ooh. Um, am I holding us back right now?
Well, we've got next class to catch up on it, and we're
Okay.
we're pretty close
Yeah.
to where I wanted to be.
You said what?
Yeah, let's go ahead and move on. There's still good
Okay.
questions though, like they're helping people realize how polar versus rectangular works.
Okay. Thank you.
So now we're looking at going through the calculation backwards. So now if we're being given a rectangular point, how do we convert back to the polar point? And this is where things get a little more interesting. So slide 16 here is a list of all the quadrantal angles. So these are when the angles are going to be the cardinal directions, 0, pi over 2, pi, and 3 pi over 2. So if we're at one of those polar angles and our radius just moves positive in one of those directions, then just plotting that point, we can then think about, all right, what's the XY point to get to that same location? And we have our radius is either positive X, positive Y, negative X, or negative Y. And so we just make the appropriate positive or negative designation. The interesting thing here is in quadrant one, um, the polar point is a comma 0, and the rectangular point is also a comma 0. So we actually have any point on the positive x-axis, the polar point and the rectangular point can be written as the same number pair. But that can get a little confusing. So it's more like watch out if it's that particular axis. So if we happen to notice the angles are one of these extremes, like we can jump to the answer quickly, but most of the time, what we actually do is we just use our right triangle trigonometry. So on this slide here, 18, I'm going to draw back in the x and the y. So with my x and my y coordinates, I've got that adjacent and opposite side, and my radius is the hypotenuse. So one of the things that relates x and y to r is I don't actually like the formula they wrote. I prefer x squared plus y squared equals r squared, because we know polar points can spit out a positive radius or a negative radius. Now, something that relates theta with x and y is our tangent function. So the tangent of theta is y over x. So those are the two other formulas I give you for the polar coordinates. So when I'm working from a polar point, from an XY point, and I want to know what the polar point is, I use these two formulas because I can put in the X and the Y numbers and calculate R. I can put in the X and the Y number in the tangent formula and then use inverse tangent to calculate theta. But when I use these two formulas, there's a little caveat to it. We have to pay attention to, did I want the angle that the formula spat out, or did I want the angle plus pi? Did I want the positive radius or did I want the negative radius? And all of that will depend on where the XY point is. So inverse tangent, when we use that as a function, only spits out answers from negative pi over 2 to positive pi over 2. So sometimes you have to add pi to the result that comes from the formula. So we'll see next class how to actually run these calculations, and then we'll take a look at some of the crazy graphing that happens in polar. You're not going to have to actually graph a polar equation on any of the tests, but I just want you to see like some of the cool shit that polar graphs can do. But it would be helpful to go ahead and try the calculation on the next slide, see what you get for the x and the y, see if you can get the answer, and see if you can make sense of that answer. But we'll do that next class.